As with all our methods, we now have equations flying all over the place. So this lecture should be the one that brings peace and harmony to all this, and will show you step by step exactly how to implement the method, along with a few tips and tricks that I've picked up over the years. One thing I'm going to introduce, and it always seems to introduce some confusion, is something that I call the 2x grid technique. And I'll do my best to explain it, but I think if I didn't explain it, you would come away even more confused with how to build devices on the grid. The next thing we need to know before we get into the method is how to calculate the grid parameters. So this is how many cells do you need to get an accurate answer. We need to answer all that kind of stuff. Then we need to talk about constructing your devices on the grid, which ties together the above two things. How big does the grid need to be? How many cell size? What cell size do you need? How do you do that in a way that coordinates placement of all the field components, etc., etc. Once we have that, then we can step through the basic finite difference frequency domain algorithm, and we're going to do it in pretty fine detail. At the end of this lecture, as a bonus, I'll step you through how to do waveguide problems with finite difference frequency domain. And the real purpose behind that is to show you that this is a very flexible algorithm. It's not just for periodic devices that have plane wave sources. We can do any number of things with that. And then we'll summarize it with a one-page summary of the algorithm. On to the 2x grid technique. So in order to do something that we call loosely building a device on the grid, we start off with what should the device be, and in this case we just want to build in some kind of dielectric cylinder. Then we calculate our grid. We know we have multiple cells. We know there's the staggered placement of the field components, so there's a staggered placement of the material properties, and somehow our device will be overlapping all of this. So the ordinary grid, the standard grid that we've been talking about, we're going to call the 1x grid. The next step then is to construct all of our material arrays. So we have epsilon xx, epsilon yy, epsilon zz, mu xx, mu yy, and mu yz, and all 6 of those exist at different points. And so potentially they look a little bit different, particularly at the boundaries. When there's a curved boundary that ends up slicing through the middle of a Yee cell, that places some components outside the material and some inside. So at the boundaries they can differ a little bit, and somehow we have to figure out a way to coordinate all this in a way that's easy and manageable. Doing it the conventional way, that's not easy, and that's pretty difficult. So as an alternative to this, I'm going to introduce what we call the 2x grid technique. And it's simply this. It's just a way to calculate where everything goes and to place everything on the ordinary grid. And after that, once your device is on the grid, the whole 2x grid thing is gone. We don't touch it anymore. And very often I see students write codes when they calculate fields and they're analyzing transmission and reflection. They go back to 2x grid stuff. And it's just a very temporary thing that we do. We start off with our ordinary grid. We calculate its size, cell size. We very temporarily create this other grid at twice the resolution, build the device on that, and then parse everything down to our standard 1x grid. And then it's gone. It does not exist anymore. So it is only a trick for building devices on the grid. After that, it does not exist and is not used in any part of finite difference frequency domain. Just as a review, here are the Yee cells. We have the three-dimensional Yee cell on the far right, and we understand that that reduces down to the two-dimensional Yee grids in the middle, and we recognize those as two slices through the standard Yee grid. And then we also have the 1D Yee grids on the left. In this lecture, we're going to talk exclusively about the 2D Yee grid. So now let's visualize a two-dimensional Yee grid. And so I'm drawing, let's see, 1, 2, 3, 4, 5, 6, 7. I'm drawing a 7 by 7 grid. And we have an EZ component, we have an HX component and an HY inside each cell. So then we repeat that and we get this overall 7x7 grid. So rather than keep drawing in 3 dimensions each time, I'm going to draw the same grid, a 4x4 version of it, this way, where this blue circle is my EZ component, and in this case it's pointed in and out of the board. Then we have our HX component and the HY component. So we'll proceed with this. So now let's introduce the 2x grid and what is meant by that. So here we are at our conventional grid. Each one of these squares is one cell, and we understand that our field components are staggered due to the Yee grid. Well, notice the placement of this. Isn't this sort of like we're getting twice the resolution, since these are placed at intermediate points in the grid? And that's exactly it. We really are getting, in a way, twice the resolution. So why not create a grid exactly at twice the resolution? So it'll have twice as many cells, but represent the same physical space. And that is the 2x grid. So here we're drawing the standard 1x grid and this dielectric cylinder that we want to put onto it. We're then going to calculate a second grid that has exactly twice the number of points. So the grid resolution parameters over here will be exactly half what they were for the 1x grid, but it's representing the same physical amount of space. So if I were to overlay this dielectric cylinder, this is the same exact size. It's just with twice as many points. So we have our 1x grid, and we'll calculate all the rules of thumb to figure out how big that needs to be, etc. We will then construct a 2x grid, something that has twice as many points, and the resolution parameters will be halved to represent the same physical amount of space. Then we're going to forget everything about Yee grids, which is really the good part about this, is we don't have to worry about, at this point, anything staggered. We'll just go ahead and build our device on the 2x grid as if we don't know anything about any kind of staggering. So here's the 2x grid and our dielectric cylinder. One way we could do this is just some kind of binary fit where either there's dielectric or there's not, and we, as best as we can, approximate the boundary of the circle. Another thing we could do is do some kind of dielectric smoothing around the boundary. And in fact, this does work a lot better. It's a little bit trickier. It's an extra step. It's not too bad, but I wanted to point out that this is also possible. For this class, we can just get away with doing something like this. We don't have to do the dielectric smoothing. Now we need to go back to, once we built this device on the 2x grid, we need to go back to the 1x grid, and now we need to understand how the fields are overlaid. This is a little bit weird, but in fact it comes down to very, very few lines of code. So we're going to go from this 2x grid where we didn't know anything about any kind of staggering. We built our device on it. Now we need to just extract all of our material arrays from that one array on the 2x grid. So this is a great picture. It shows the dashed lines show the divisions between the 2x grid. The thick black lines show a cell on the 1x grid. And of course we see our field component placement. And then we also show the dielectric cylinder. And we can see now very clearly how when the structure itself slices through the middle of a grid, some components can be inside the material and some can be outside. An example of that is this second cell here. Even though what I'm outlining now is one cell on the Yee grid, we can see that the HX and the HY component, one's inside the material and one's outside the material. So clearly, whatever material properties we assign to HY are going to be different in this cell than they are for HX. So let's look at how to sort all this out. This step I call parsing the 2x grid onto the 1x grid. So we're going to go from a single 2x grid, there's one device built on a single 2x grid, and potentially we extract all 6 material arrays from that, the epsilon XX, epsilon YY, epsilon ZZ, mu XX, mu YY, and mu YZ. Mu ZZ, sorry. Now for the E mode, it turns out the only thing that retains is the ERZZ, URYY, and URXX. The other mode would have a URZZ, an ERYY and an ERXX. But let's just focus on the E mode, and it'll be clear what you do for the other mode. So down here is a repeat of the picture from the last slide, and we're going to look at what to do with this. But from this one device built on the 2x grid, where we didn't know anything about staggering, somehow now we need to construct 3 material arrays, our ERZZ, URYY, and ERXX. So let's start with the ERZZ. We're going to go one cell at a time. We're going to see where the ERZZ component lies, and it'll be at all of these blue circles. And we're going to go one cell at a time. So we look at this first cell, and we see it is not inside the material. So we go up here, there's no material in that first cell for this ERZZ array. Then we go to the second cell. There is no material on top of that component. So we go up here, we fill in the entire cell without that material. We could say the same thing for this entire row. So in fact, the entire top row here does not have any materials in it. Now let's look at the URXX. We start off, now we're in a slightly different position within that first cell, and there's no materials assigned to it. So it's probably free space out here, and we plug in no material here. Now we go to the second cell. Suddenly, it's inside the material. So in fact, in this array, we're going to fill in this whole cell with material. Now we go to the third cell. That HX component is still inside the material, so we go over here and we fill in the entire cell with material. Now we go to the fourth cell. It's no longer inside the material, and so we don't put it here. Now notice the first row here and the first row in so the first row in ERZZ and the first row in URXX are different because they're at physically different positions. The device happened to slice through the middle of the cell, and so their arrays look a little bit different. So let's look at finally URYY. Well, now we're looking at these positions within the E cells. In the entire top row, there's no materials. So no materials. And we will notice that this component happens to be different. We'll look at this column of cells. So no material, no material, no material, no material. So no material all the way down. But if we go look at that same column for ERZZ, we see it's not inside a material. Here it is, and here it's not. So no material, 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 no material. So we can very quickly, as you'll see, extract the 3 material arrays that we do want from this single array on the 2x grid. So here's how it's done. If we are on a 3x grid, we're going to have one array describing our relative permeability, relative permittivity, and one array on the 2x grid describing the relative permeability. Now from this one array on the 2x grid, we extract 3 on the 1x grid. So we go from one array on the 2x grid to 3 arrays on the 1x grid, ERXX, ERYY, ERZZ. And notice all 3 of these are taken from ER2. Just like we have one array for the relative permeability on the 2x grid, and we extract 3 arrays from that are on the 1x grid. Now the way we do this is we go from some number in steps of 2 all the way to the end of the grid. Starting from some number in steps of 2 all the way to the end of the grid. Starting at 1 in steps of 2 all the way to the end of the grid. And in fact, this :2 : NZ2, that same form appears everywhere. The only unknown and the only thing that changes between all these is this first number. And so that's asking the question, where do we start in the cell? And that we go back to the previous side and you look at whether that particular component is the first in the cell or in the second position of the cell. And you do that for X, Y, and Z directions. Now for our E mode that we talked about on the last slide, here's how we do the extractions. We'll have one single array on the 2x grid for the relative permittivity, and for the E mode anyway, we only need one from that. There is an ERXX and ERYY, but those are used from the H mode. And this line of code is exactly like this line of code up here just without the z dimension, because we're only talking about 2 dimensions here. I'm sorry, it's actually this third line that it reproduces, because it's ERZZ we're extracting. So we just erase that, and what's left, we'd have what we would say for a 2D array. But anyway, from the single relative permeability array on a 2x grid, we extract 2 of them for the E mode, URXX and URYY. And so look at these starting indices, go back to the last slide and see if you can see why, because of where they're starting, those are the numbers that we choose. And then for the H mode, here's where the other 2 arrays for permittivity would come up, XX and YY. And then for the H mode, we only need 1 relative permeability array, the URZZ. So very often what I'll do is I'll extract all 6 of these, and then just later down in the code is where I distinguish between the 2 different modes. This is really fast. So we go from a 1x grid and calculate a 2x grid, twice the number of cells, half the resolution. We forget everything we know about Yee anything or any kind of staggering, build the device on that 2x grid. Then with these chunks of code, we immediately go from our 2x grid to the different material arrays we need at the 1x grid, and now all of these take into account in these simple lines of code where everything lies on the grid. And so while this seems a little bit strange, it is actually much easier than if we didn't do that, and you'd actually have to go build the device on each of these individual 1x grid arrays and figure out where they lie. I think that's a much more difficult task. Okay, so we finished the 2x grid thing, and now we sort of want to go backwards a little bit and figure out how to calculate these grid parameters. How many points do we need? What resolution do we need? So here we go. Here is the overall grid strategy. We tend to place the device somewhere in the middle because we want some space between our device and the PMLs. Now why is that? Because there's going to be evanescent fields associated with this. Fields that aren't radiating away, they're not going anywhere, but they do stick outside the device and they exponentially decay. We don't want those evanescent fields to couple to the PML. And this is something we'll talk about a little bit later, exactly why that is. But we want enough space so that any evanescent fields, any fields that are stuck to this device and not going anywhere, will be completely contained within the grid and not touch the PMLs. So we need a space of about a wavelength on either side. Assuming we're modeling something periodic, we're going to put periodic boundary conditions on the left and right sides. And we probably want PMLs on the top and the bottom. And I find usually about 20 cells works well. So here's our overall grid. And we'll need Dirichlet boundary conditions at the top and the bottom. Because if the PML is doing its job, the fields decay, and they are about 0 by the time they get to the boundary. And so the Dirichlet boundary condition works well. So here's our overall grid strategy. This is the 60,000 foot level of what we want to do. But we still have to put numbers to a lot of this. So the first thing, what grid resolution do we need? And so I'll start off by saying that there is no equation that I can give you so that you can calculate the size of the grid and the grid parameters that'll work. All I can give you are some rules of thumb and things that work well, but the real answer comes from something called convergence. We'll talk more about that in the next lecture, but the short answer to convergence is you'll model your device and you'll get an answer. Then you'll increase the grid resolution. Use more points. It'll take a little bit longer, but you resimulate it, and you keep doing that. You keep adding points and simulating your answer, and then you'll plot your answer as a function of number of points in the grid. And what you'll see is that answer will swing around, but it'll eventually converge, and it's kind of up to you to figure out where it's converged. And very often you could add more points and get better accuracy, however it's taking a long time. It's up to you to figure out where that trade-off is. But convergence is the way, the rigorous way to determine these numbers. Everything else that I'm going to give you are just rules of thumb so that you can make a really good first guess as to grid resolution and stuff like that. So here we go. there's two things we need to consider when calculating how big those cells or how small those cells need to be. First of all, we know we have a maximum frequency or a minimum wavelength. We also know that there's a maximum refractive index somewhere in your grid. Well, that minimum wavelength inside that maximum refractive index actually becomes an even shorter wavelength. We usually want to resolve that with at least 10 grid cells. So we have our first rule. Our grid resolution based on wavelength needs to be the smallest free space wavelength that you plan to simulate divided by the maximum refractive index anywhere in the grid. So this gives you the shortest wavelength that your model will see anywhere. And then we want to divide that by a number that's at least 10, 20, 30, 40. I've had models that needed 200, and we needed lambda over 200. But this is just one consideration. You want to resolve the minimum wavelength. Another thing we need to do is resolve the minimum structural dimension. So if we have a little tiny feature hanging off our device, but may be really important, we want to resolve that with at least one grid cell. Other times you'll read at least 3 grid cells, and it's up to you to figure out really what that number needs to be. But it's on the order of 1, 2, or 3. And so we take this minimum dimension and we divide it by a number that's 1, 2, 3, maybe even 4 sometimes. And we get another guess as to what the size of the grid needs to be. So what we actually use, or start off with anyway, we'll look at these and we'll take the smallest one. So we look at the minimum value between the wavelength limited resolution and the minimum feature size limited resolution. Take the minimum one and we'll set our grid parameters to that. And that's just our first guess. We're going to refine this in the next slide. The next step, I like to call this snapping the grid to some critical dimension. So suppose from the last slide we calculated a delta x and delta y, and it would form a grid that looks like this, and just 4 cells vertically through the grid somewhere. But suppose we have a device that has this as a dimension, this vertical line, and we must resolve that as accurately as possible. Well, we see we messed up a little bit calculating our delta y parameter, and we can't get this dimension represented exactly. Well, what we can do is shrink delta y until this boundary lies right on this dashed line. And when we do that, we have represented that dimension exactly. So what I like to do is we have the ability to pick 2 critical dimensions. Pick one along x and one in y. And it's up to you as the engineer to figure out what is the critical dimension. If you're modeling a diffraction grating, in the x direction, the critical parameter is probably the grating period. In the y direction, it's probably the grating height or the depth of the grating. So it's up to you to figure out what are the critical dimensions. But given those, we simply adjust the grid resolution to compensate. So here's how we do it. We take our critical dimension and we divide by the grid resolution that we calculated on the previous slide. This probably comes out to have something with a fraction in it, some kind of decimal, because we didn't guess quite right. So let's say we come off with 3.5 cells. What I'll do is I'll round up and I'll say I want to resolve that dimension with 4 cells. And here maybe we do the division and I end up with 20.7. Round up and I'll say I want to resolve that critical dimension with 21 cells. So now that we have these integers, we just tweak our resolution parameters again by saying the critical dimension divided by the number of cells we just calculated. And now we're guaranteed to represent these critical dimensions with an exact number of cells in the grid. Now if we have 2 critical dimensions within the same axis, you're going to have to just choose one or the other, or make one an integer multiple of the other, or something like that. All we calculated on the previous slide is the size of the cell in the grid resolution parameters. Next, we need to calculate how many cells we need. So here's what we need to consider. We need to have enough cells, first of all, to fit the device. We also have these spacer regions. Remember, the device and the PML need to be separated by some amount of space. We have to include that. and of course the PMLs. And we have a spacer region and a PML on the top and the bottom. So putting all this together, what does this look like? We have the size of the device in the X direction, or the horizontal direction. We will divide that by the grid spacing, and normally what we do is we round that up and we figure out how many cells wide the grid is. And we'll see when we get to the code a little bit better how that is handled. But the other thing I want to mention is that we always want to make this number odd. So the number of cells wide the grid is needs to be an odd number. And that's because we want symmetry when we're calculating our spatial harmonics. We want to go from, let's say, -5 up to +5 and passing through 0. So that would be 11 points. And I can make that argument. So we have an even number, then we cannot pass through 0 and have an even number of spatial harmonics on the negative and positive side. Now it is absolutely possible to write a code that can handle an even number of points, but I think it's just simpler to just make it odd. Then in the vertical direction, we have the same thing. We have our device divided by the number of grid cells. That'll lead to the size of the grid cell. This will give us a number of how many grid cells tall our device is. We need to add 2 PMLs and 2 spacer regions because we have top and the bottom. And for each of these, we always want to round up. So here we may end up with a fraction, so we'll round up. For these spacer regions, what I like to do is figure out what is the longest wavelength that we're interested in. We'll divide that by the refractive index in the spacer regions, and then also divide that by the grid spacing in the vertical direction, and then round up. And that's a good estimate of how many cells we need for the spacing. But remember, the real way to determine that is to look for convergence. We'll keep making it bigger and bigger and bigger, and when your simulation doesn't change much anymore, we'll say that's been converged. So these are just good rules of thumb as a good first guess, but convergence is the real answer. And we'll talk more about that next lecture, for sure. So now we know the size of the cells and how many cells. So the next thing we need to do is calculate the 2x grid. Well, that's real simple. It just has twice as many cells, and then in order to represent the same physical amount of space, the resolution parameters are halved. So 4 lines of code, we now have our 2x grid. Next major step is building the device on the grid. So let's just dive right into this. Now we've talked about this before. All real devices are 3-dimensional. We've just formulated and will implement a 2-dimensional code. So what is meant by that? Well, our device, if we can reduce it to 3 dimensions, has to have a dimension that is uniform, like we're extruding it. And so we'll call this the Z direction. And then we have another direction where in this case, we're using periodic boundaries. So we go ahead and pull out a unit cell from this. The unit cell is this little tile, if you will, so that if you stacked it onto itself, you would reconstruct this grading. We'll use periodic boundary conditions on the left and the right. We'll definitely be using periodic boundaries or absorbing boundaries at the top and the bottom. But the Z direction right now, in and out of the board, is extruded and infinite and uniform. So anytime we run a 2D simulation, in fact, it is a 3D simulation, but with that third dimension being long, extruded, and uniform. There's another way that we can reduce 3-dimensional problems to 2 dimensions using something called the effective index method. So let's say we have this configuration of dielectric waveguide. So this might be some kind of optical integrated circuit, for example. We have some kind of dielectric substrate, a little dielectric rib here, which forms a waveguide, and some kind of weird coupling network. Well, if I look at a cross-section away from the waveguide, that has some average refractive index associated with it. If I look at a cross-section through the waveguide, that has another average refractive index associated with it, where this one will be a little bit higher than outside the waveguide. Well, I can take these two effective refractive indices and build a 2-dimensional grid this way, where it looks like the top view. And in fact, this is a very, very accurate way to model waveguide circuits. But it is an approximation, and it's a whole other way that we can reduce things down to a two-dimensional problem. Okay, so we calculated our 1x grid parameters. We then very quickly calculate our 2x grid parameters. Now it's time to assign materials to that 2x grid. And we mentioned before that we could actually use one of two ways. One where we just throw in any kind of material values, just either as material or not, and this is the easiest. The other way is that we can average the dielectric values around the perimeter. This is actually better. This leads to faster convergence, meaning we can get away with larger grid cells, faster simulation for the same amount of accuracy. So this is simpler to build, but will require a bit higher grid resolution. This is a bit more complicated to build, but we can get away with coarser grid resolution. I really don't expect anybody in this class to do the smoothing operation, and we can just build the materials directly on our grid, and we won't have to worry about it too much for what we're modeling in this class. But if you ever take these tools and do something else with it, and suddenly you're modeling things that are very large and very complex, the smoothing is a great way to get away with fewer number of cells, so things run faster. So before we conclude this, we definitely want to talk about metals and how to handle metals and get them in your grid correctly. The absolute easiest way to build metals into your grid is just to set the dielectric constant wherever there's a metal, at whatever point in your grid that has a metal, to something ridiculously large and negative. And that is the same thing as putting in a metal. Something that works a little bit better, if you want to build in a perfect electric conductor, what you'll do is you go down your column vector of the electric fields, and you'll find the one that needs to be embedded in metal. Well, electric fields are zero inside metals, right? So what we do is we make this entire row zeros, and we put a 1 in the diagonal position, and then we put a 0 over here in the source column vector. So this entire equation now just reads that that particular electric field is set to 0. So we replaced whatever finite difference equations in that row with a new equation just setting that field to 0. I think it's still a little bit easier just to set the dielectric constant to something ridiculously large and negative. So now let's talk about how we place the metals. And the big rule of thumb here is that the first component inside the metal has to be a tangential component to the interface. And I could say the same argument about something where you go from, let's say, air to something that has a really high dielectric constant. You're going to want that first component inside that material with high dielectric constant to be tangential to the interface. So let's look at a bad example. The gold here is representing a region in the grid where we've placed metals. Well, look at the first field components inside. Those are actually normal to the interface. This is bad. This is going to lead to very, very slow convergence. So don't do that. A better way to place it is this way, where the first ones right inside the metal, or even a high dielectric constant, are tangential to that interface. This will converge much, much faster. But notice in doing that, we're actually requiring then that it slices through the middle of some of these cells. That way this tangential component here is tangential to the interface, but this component is perpendicular. These are in the same cell, but one's inside the metal, one's not, and it forces us to do things like this. Now when I incorporate metals, I tend not to use the 2x grid technique, and I build the device separately on all of the different material arrays because I think it gives me a little bit more control, whereas the 2x grid technique is a little bit abstract when you don't necessarily care about doing this. And for low to moderate index contrast devices, the 2x grid technique works really well. So that's a short story with metals. Now we're in a great position to start all over again and talk about the finite difference frequency of an algorithm one little step at a time. And that's what this section will do. First of all, we have to prepare all of the data that our FDFD algorithm will need to run. And it needs a few things. Well, it obviously needs the materials put onto the grid. It needs to know what device it's modeling. So we're going to have to build two different arrays, two different two-dimensional arrays, and both of these are on a 2x grid. One has the relative permittivities, and the other has the relative permeabilities. So given these, MATLAB will know how big they are, so we also need to provide the cell size, the grid resolution parameters in X and Y. And these can be different. We like them to be as similar as possible, but they can be different. We also need to tell it how large the PML regions are. So we'll define one on the Y low side and the Y high side. So in other words, the top of the grid and the bottom of the grid. And we'll give those numbers in 1x grid terms. So 20 cells is 20 cells. FDFD will need to know the free space wavelength of your source. It will need to know an angle of incidence, assuming we're using a plane wave source. This doesn't make any sense if we're exciting waveguides, of course. And it will need to know what mode or polarization we want to model. So this is the E or H mode. So that represents all of the data that your FD algorithm will need. Given those arrays, ER2 and UR2, the first thing we'll need to do is figure out what are the material properties where we're injecting the source and where we're calculating reflected and transmitted fields. So what I like to do is look at the top row, which the way we're doing things will need to be homogeneous, and the bottom row, which will need to be homogeneous. So we'll extract the permittivity from the top and bottom rows, and we'll call this permittivity in the reflection region, permittivity in the transmission region, and we'll do the same thing for the permeability. We'll extract it for the reflection region and transmission region. Remember, the way we're formulating this with a plane wave source and the way we're calculating transmitted reflected power requires that the reflection and transmission regions are homogeneous. So our device cannot be here. We need to have all the same values in the horizontal direction. We can have all kinds of craziness in the middle, but at the edges, where we're calculating transmission and reflection and injecting the source, must be homogeneous. Now that isn't an absolute requirement, but we would have to do our sources and power calculations differently. The next step in this algorithm is to calculate all the different wave vectors, and we're in a position to do that because we know the material properties in those regions. So we can calculate the free space wave number. We can calculate our incident wave vector. We'll know the period of our device, so we can calculate the entire expansion of transverse wave vectors. It's an expansion because we're using periodic boundary conditions. Then we can also calculate the longitudinal components in the reflection and transmission region. Notice there's a negative sign for the reflection region and not a negative sign for the transmission region. That's because this wave is propagating backwards, so we have to put a negative sign in here. The next thing we need to do is calculate all of the PML terms. So since we only have a two-dimensional grid, it's just calculating S sub x and S sub y. Now if we're using periodic boundary conditions on our x low and x high boundaries, then this is going to be ones everywhere. In fact, we don't even really use it. Our S sub y, however, will be ones all through the problem space, but then out here it's going to do something different, and the imaginary component will increase. And notice we have this sort of graded profile. And I like to make my PMLs about 20 cells. Sometimes there's times we need more. Other times we can get away with a little bit less, but I tend to set it to 20 and never really think about it after that, assuming things are working. Once we have our PML parameters, Sx and Sy, then we incorporate those into our material arrays. So we built our material on the grid, we calculate the PML, then we multiply these together. And what we come away with are an adjusted version of our materials that now have loss built into the boundaries. So here's how we modify all of those, the tensor elements with the PML parameters. And I like to calculate the PML on the 2x grid and incorporate it there. That way, we don't need to think about where the PML parameters need to be for the different components because they're in different physical locations. So I usually build a device on the 2x grid, incorporate the PML, and then parse it down to the 1x grid. So in fact, that's the next step. Incorporate the PMLs, then we parse it down to the 1x grid. And we talked about that earlier. Once we have our arrays, so that they're in the form now, we could plot them to the screen and we could see our device and even see our PMLs. Now we need to form our diagonal material matrices. So in MATLAB, I like to do it this way. This first part, ERXX, and then in parentheses a colon, this converts it to a column vector. The next thing I do is put a sparse function outside that, which makes it a sparse column vector. Then I use the command diag to place that sparse column vector into a matrix. Now, the reason we make it sparse is so that when it puts it into what we call the diag command, it creates a sparse matrix. If we reverse these, and in principle we could, the problem is what it's going to do is it's going to create your entire huge matrix, which might be 500,000 by 500,000 elements, and it's going to store it as a full matrix, and you're going to run out of memory and melt your computer. But as long as you say it's sparse first, then insert the diagonal, there's usually no problems at all. When all is said and done, they look like this. There's zeros everywhere except numbers going down the diagonal. And these are all your epsilon XX components over the entire grid. So we do this 6 different times to calculate epsilon XX, epsilon YY, epsilon ZZ, mu XX, mu YY, and mu YZ. Now we have our diagonal material arrays that we can use to build our matrix wave equation. The next step is to construct our derivative operators that operate on a Yee grid. We're going to write a function called Yee-dir that will do this, and we're going to give it a number of input arguments. The size of the grid resolution parameters, what boundary conditions we want. Is that Dirichlet? Is it periodic? And then if it is periodic, it needs the incident wave vector. Now when we actually call this, because we've normalized our parameters, we want to multiply the grid resolution parameters by k0, because that's how we're normalizing them. This effectively divides everything by the wavelength. And then we want to take our incident wave vector and divide by k0. So we're handing Yee-dir all the normalized parameters, and out come our derivative operators. We have 4 of them with normalized parameters built into them. So this is going to be one line of code in MATLAB that will construct your derivative operators. We have our diagonal material matrices and our derivative operators. We have everything we need now to calculate our wave matrices. And this is the wave matrix for the E mode and a very similar wave matrix for the H mode. Notice they look very similar. This is another single line of code of MATLAB to do that, and I think I even provided it for one earlier in this lecture. So now we have our wave matrix. Now on to the B, the source vector on the right-hand side of our matrix equation. So the first step in calculating that is to calculate this source field. We're going to fill in a grid with the same material that exists where we inject the plane wave source. And if everything were that material, what would the source look like without having a device present? So our source field tends to look like this. It's a nice uniform field coming in at some angle. And we calculate it this way. Then once we have this on a 2D array, we reshape this to a column vector so that f sub source is a column vector. Now we know the source field at every point in our grid. Next, we calculate this scattered field masking matrix. So I like to go ahead and fill in a grid and place zeros everywhere that I want to be a total field quantity and ones everywhere I want to be a scattered field quantity. And for the way we're constructing this, where we have periodic boundary conditions left and right, I usually make this scattered field the size of the PML plus 1 or 2 more layers. And that plus 1 or 2 more layers is where we're calculating the reflected fields and injecting the source. Once we have this, we reshape this into a column vector and then insert that 1D array or that column vector into the diagonal of a matrix. So the scattered field masking matrix is zeros everywhere except the diagonal, and the positions along the diagonal that correspond to positions in the scattered field will have 1s. Once we have that, we very quickly now can calculate our source vector B. It's just Q times A minus A times Q times F source. And once we have B, now we have a big matrix equation that can be solved. So the next step is to solve that. And this is the shortest, simplest line of code in your MATLAB program. Now, interestingly, everything up to this point, while it seems very involved, it runs in the blink of an eye. Everything comes to a screeching halt when we type in this command. So our shortest command is by far going to take the longest amount of time. So what we call MATLAB, we calculate F, and remember here, we're definitely not going to calculate the inverse of A. We're going to say A backward divide B in MATLAB. And once we get that, we're going to have our answer, our field everywhere, in the form of a column vector. Don't forget to reshape that back to the 2D array so you can visualize it. So we reshape it back to the 2D array, and we're going to have our fields throughout the entire grid. We're going to have our PML overlapping some of these. Just outside our PML, we want to extract the fields in this cross section, and we're going to use this to calculate the reflectance. Then on the bottom, just outside the PML, we want to extract the cross section here, and we'll use this to calculate transmittance. We don't want to take fields from inside the PML because the fields have already been absorbed a little bit by there, and we're not going to be able to account for our energy. So we need to be outside the PMLs, but pretty close up against them. Now once we have these, we're going to need to remove any phase tilt if we've incorporated any kind of angle of incidence. Remember, we're going to take an FFT of the field because it's periodic to calculate the amplitudes of the spatial harmonics. However, remember, it's really not the field that is periodic in that regard, it's the amplitude portion of the wave. So our total electric field is not necessarily periodic. It's only going to be perfectly periodic at normal incidence. As soon as we build any kind of angle of incidence, this is no longer periodic. And we have to express it as an amplitude term and a phase term. This amplitude term is the thing that's periodic. So when we extract our fields, we need to somehow isolate just these amplitude portions and get rid of these exponentials. So let's solve these equations for the amplitude terms. And here we are. So the way this works is you'll extract your electric fields, and then you'll multiply by this exponential to remove the phase tilt. And we'll do the same thing here. So we'll extract the fields, multiply by this phase term with opposite sign, and that will now cancel that phase tilt and give you purely the amplitude portion of the electric field. That's what we can Fourier transform. So that's exactly what we do. We're going to use this concept of the plane wave spectrum, where if we have a periodic field, we can think of that as a sum of plane waves all at different angles. Also remember, these higher order ones are probably evanescent. Usually only the lower order plane waves are actually plane waves. The rest are evanescent. So we take these amplitude terms now and we FFT them. What comes out of the FFT are the amplitudes of our spatial harmonics. And we do that for both the reflection and transmission sides. Now, here's the trick in doing that. We calculate the FFT, that's pretty straightforward. Because of the way MATLAB calculates the FFT, it's scaled by the number of points. So we need to divide by the number of points to scale it correctly. We also want to center it with the zero order mode being in the center of the array. So we have to do an FFT shift. And it also turns out it's still going to be backwards relative to how we want. We want that first element to be, let's say, the negative fifth. It'll be we want it to be the negative order spatial harmonics followed by the positive. So we also need to flip it to enforce that. But then we come away with two 1D arrays that contain the amplitudes of all of our spatial harmonics. Now we have all the information we need to calculate the fraction efficiencies associated with each spatial harmonic. Well, one thing we did, we made our source have unit amplitude. So this S int squared just equals 1. And in fact, we don't have to write it in our diffraction efficiency equations anymore. So dropping it, our diffraction efficiency equation becomes this. These longitudinal k components we calculated at an earlier step, so they exist. This top one here, notice the index m, this will be a 1D array. We're going to divide it by this single scalar number. This will also be a 1D array. We're doing a point-by-point multiplication here. When we're done, this comes out being a 1D array containing the diffraction efficiencies of all the reflected modes. Likewise, we have to calculate the diffraction efficiencies for all the transmitted modes. So here is our 1D array, ky trn with subscript m. These other three parameters are just scalar numbers. So this entire thing will be a 1D array. And then we multiply it by a 1D array. Those are the amplitudes of the spatial harmonics. And we get the diffraction efficiencies of the transmitted modes. Now we use this equation if we solved our matrix equation for electric field quantities. If we didn't, if we solved them for magnetic field quantities, this is the equation we have to use. It's the same equation except epsilons instead of mu's. And also remember, we assumed that S int equals 1 in these equations. It's absolutely possible to deviate from that if you wish, but then we have to plug S int squared down here so that the math works out. The last thing we want to do is calculate the overall reflectance. So the overall reflectance is clearly the sum of all the diffraction efficiencies of the reflected spatial harmonics. And the overall transmittance is the sum of the diffraction efficiencies of the transmitted spatial harmonics. And then the final last step, we add total reflectance to total transmittance, and assuming we have not incorporated loss or gain, we should get 100% of our energy back. If there is loss, that'll clearly be less than 100%. If there's gain, it'll be probably greater than 100%. And if you have both, well, who knows what it's going to be. But even when you have loss or gain in your model, I always recommend at least run one simulation with the loss and gain turned off, check for conservation of energy, and then turn it on. So that's it for the finite difference frequency domain algorithm. I have a bonus section coming that'll talk you through how to do waveguide problems. We're not going to do that as part of the required part of the course, but you might want to do it as a project or something. So here we go. For waveguide problems, we typically put PMLs all the way around. And in this case, we're modeling some kind of waveguide that has a bend. Maybe we're trying to figure out the minimum bend radius, because the tighter it bends, at some point it begins to leak. So what we do is we will define some kind of window just outside the PML, like we did before, and another window just outside PML. So in a way, these are like our transmission reflection regions again. So we want to extract the materials here. We want to analyze these cross sections. So recall when we had our waveguide lecture, we learned how to analyze slab waveguides. Well, when we extract on the previous slide, when we extracted those two regions, and we said they're kind of like our reflection transmission regions again, those are slab waveguides. It's a one-dimensional model with a core somewhere in the middle of it. So we go back to those codes and we analyze those waveguides and we calculate all of the possible modes that can exist in those windows. And we see a whole bunch of them. So a lot of them look crazy like this. What this really is telling you is that there's waves external to the guide. These are plane waves that are just sort of passing through and not really affected too much by the guide. We have other things that look kind of like guided modes, but they have stuff going on the outside. These are more like your leaky modes. They're kind of guiding energy, but they're also leaking out. And this is reversible too. If you have energy on the outside, it'll sneak into the guide. Then we have the true guided modes. They go off to 0 at the outside. So these are actual guided modes. And those are the three things typical of what you'll see if you visualize the modes that you calculate. So we're going to calculate at both of those regions that we talked about on the last slide. So let's interpret this a little bit. It turns out that your field can look like more than what is in those modes. So here's your Eigen-Modes, and let's say the field in the actual cross-section look crazy. This doesn't look like any of these modes. However, one thing that has to happen is whatever the field looks like has to be some kind of integer combination of all the Eigen-Modes. I'm only showing the guided modes here, but in fact it's all the other ones too. There has to be some integer not integer, but some combination of those with these complex weights that would all add up to give you whatever the field is here. So we take all these complex weights and we make a column vector out of them and just call it A. So in this case, since it looks mostly like this first order mode, that's probably going to be the biggest number. And we just look at the weights on the other ones and we can figure out what they are. And they'll get smaller and smaller and smaller. So it turns out then the overall field has to be this eigenvector matrix that we calculated when we solved the Slab waveguide problem times this column vector of weights. So if we do the math and multiply all this out, what we see is that we have weight 1 multiplying eigenvector 1 plus weight 2 multiplying eigenvector 2, and so on. So the overall field, by multiplying the eigenvector matrix by this column vector of coefficients, is this weighted sum of the Eigen-Modes. So conclusion from this slide is the field across your waveguide has to be some linear sum of the Eigen-Modes. If we're going to source a waveguide, we probably want to source it with the fundamental mode. Well, how do we determine, once we calculate this full set of modes, which one is the fundamental mode? And so here's some hints to help you find that. We calculate an effective refractive index. If that has an imaginary part, that means it's a leaky mode and it's being absorbed. And that's very unlike a guided mode in the waveguide. So the fundamental mode usually has a very, very small imaginary part of the effective refractive index. It probably has the smallest of all the modes you calculate. So that could be one way that we find it. And the reason I say it's not exactly 0, you may have loss built into your materials. The other thing is you could have leaky modes and it could leak out. So this is going to have the smallest imaginary part. Another thing, the fundamental mode is mostly contained in the core. So the effective refractive index will be very close to the core refractive index. So I'll say that the real part of the effective refractive index is very close to the core index, a little bit smaller, but very close to the core index. Also, if it is a guided mode, the real part of the effective refractive index has to be greater than the indices on either side, the cladding refractive indices. If this weren't the case, we wouldn't get total internal reflection to get a waveguide to begin with. So we use things like this to sort through all the modes and figure out and identify which one is the fundamental mode. And of course you can plot it, and you should be able to see right away if it's the fundamental mode. It'll just have one hump compared to 2 or 3 or 4. Just like the plane waves, we need to calculate the source field everywhere. Before, we made the entire region homogeneous. It's a similar concept now, but slightly different. Let's say we're injecting our source in the cross-section that I'm moving up and down right now. Well, our source is being injected in a place that is not homogeneous anymore. So in fact, what we need to do is pretend that this device, whatever it looks like in the cross-section, is uniform all the way throughout the grid, and calculate the source that would exist there. So this is what that source looks like throughout the grid. But here it actually is overlapping materials. Plane waves don't exist unless you have a homogeneous material. As soon as it becomes inhomogeneous, plane waves no longer exist. So that's why we had to replace it with homogeneous material. Now I could say these guided modes only exist in this one particular inhomogeneous case. So we need to extend that all the way across the grid and calculate what the guided mode would look like going all the way across the grid. So that becomes our source field now for this guided wave problem. Okay, so we set up our source field. Now we can actually calculate the field, and we get a picture that looks maybe something like this. So what we'll do is we will extract the fields from this cross section and plot them, and what we see is that it's basically just noise. It's 10 to the minus 16 because most of the energy is scattered out of the guide, nothing really reflected back. That makes sense. But if we look at this cross section, we see we have a pretty strong guided mode, but some other stuff out here. So if we plot it, we see this pretty strong guided mode, but there is other stuff. Well, if we want to know how much comes out being guided, we need to figure out how much of our guided mode is in that while ignoring all the other possibilities. So how do we do that? And to do that, we go back to how we defined our eigenvectors and our amplitude column vector. So let's look at the transmitted side. Whatever our field is has to be a linear combination of the eigenvectors that we calculate in this vertical cross section. So we calculate our eigenvectors, and we have some unknown column vector of amplitudes that multiply all these column vectors that would give us our overall field. Well, we know the field. We can use our waveguide analysis to calculate these eigenvectors, so we simply solve this equation for these amplitudes. So we backward divide our field by these eigenvectors, and we calculate the amplitudes on each of the modes. Well, if we identified which one is the fundamental mode, we can go into that column vector and pull off that particular amplitude, which is the fundamental mode, and figure out how much power is in it. So given all the amplitudes of the reflected modes and the amplitudes of the transmitted modes, we can use this equation and come up with a column vector that tells you how much power, relative power, is in each of those modes. And by relative power, if there's a 10% there, that means 10% of the initial guided mode went into the particular mode that we're talking about. So we have a column vector of powers in the reflected modes, column vectors of power in the transmitted modes. These are equivalent to diffraction efficiencies of the spatial harmonics. A little bit weird to talk about diffraction efficiencies with guided modes, so we don't use that verbiage, but it's the same concept. So if we go in these arrays and we pull off the one amplitude for both of these that corresponds to the zero order mode or that fundamental mode, now we can use these equations to calculate the power in that fundamental mode that's reflected and transmitted through the guide. So here's an example, and this is a real simulation. Simulated a waveguide bend. We see a lot of power has leaked out, but definitely some gets guided. We look at the cross section for both reflected and transmitted sides. On the reflected side, we see very small numbers, and this tells us that essentially nothing was reflected. But on the transmitted sides, we get a spike that has an amplitude of 0.34. Now, we initially excited it with an amplitude of probably 1, and we get out a 0.34. So our source has this as a column vector. So if we were to weight all the modes of our source, we gave the fundamental mode an amplitude of 1 and all the rest 0. So in other words, we're exciting the guide with just the fundamental mode. Well, if we look at the transmitted side and we do our trick to calculate what all these different weights are, we see that it's 0.87 in the fundamental mode and smaller numbers in the other modes. So if we want to calculate the fraction of power that was transmitted in the fundamental mode, we'll take this weight, we'll divide it by this weight, and square it. So in this case, it turns out 76% of the power made it through that bend. So that means something like 24% has scattered out of the waveguide. So what we probably want to do is set up this model again with a more gradual bend radius and keep doing this until some 99% gets transmitted. Okay, let's wrap all this up. Here in one slide is the summary of the finite difference frequency domain algorithm. Step 1, we'll construct the problem. So define everything about it. How big is your device? What materials is it made of? we want to calculate all the grid parameters, what cell size we want, how many cells in the grid do we need. Then we'll assign the materials to these 2D arrays. We'll use the 2x grid technique to come up with the relative permittivity and relative permeability on those 2x arrays. At this point, we've constructed all the information that finite difference frequency domain needs to solve your problem. Well, the next step, and probably the first step really in FDFD, is to compute the wave vector components. So we're going to extract the materials in the reflected and transmitted regions. We'll calculate the incident wave vector, giving the desired angle of incidence. Then we'll calculate this expansion of the transverse wave vector. From that, we can calculate the expansions or the longitudinal components associated with each one of these transverse wave vectors. But we're going to have one for the reflection region and one for the transmission region because they could potentially be in different materials. Now, once we have that, we're going to calculate our PML. We will incorporate that onto our permeability and permittivity arrays on the 2x grid. Now we have everything we need to. We overlay that or parse it down onto the 1x grid. So at this point, we come away with potentially 6 different arrays: epsilon xx, epsilon yy, epsilon zz, mu xx, mu yy, mu zz. And those are all on the 1x grid. At this point, the 2x grid's done. No more of this algorithm ever involves the 2x grid, so please don't make that mistake. It's just a trick to build those material arrays. Once that's done, it's gone. Everything is just 1x grid as you would expect it, as if we never even talked about the 2x grid. Our next step in FDFD is to construct this wave matrix. So we diagonalize our material matrices. We call our function to construct the derivative operators, and once we have that, we can construct our wave matrix. Then we'll construct our source vector. We first calculate the source field that's uniform across the entire grid. We construct our scattered field masking matrix, and then we construct the source vector B. Once we have that, we can solve the matrix problem for the electric field. That should be a lowercase e here. I'll change that. So by the time you're listening to this, that will be a lowercase e. Then we know the field everywhere. Now all we do is post-process it to calculate some meaningful things. We'll extract the electric field from the reflection and transmission regions. We'll remove the phase tilt, so we're just left with the amplitude portions. We'll FFT those to calculate the amplitudes of the spatial harmonics. Now we have the amplitudes, and we also have all the wave vector information. We can calculate the diffraction efficiencies. Then we add all those up to get reflectance and transmittance, and then we add those up to look for conservation of energy. And without loss or gain, our conservation of energy should be 100% or at least very close to it. With transfer matrix method, we were dead on conservation within 0.00001% or something ridiculously small. Here, we'll be within conservation energy by numbers like 0.1, 0.2%. Not quite as good as a transfer matrix method because there's a lot more numerical stuff that could be going wrong, but still pretty close to 100%. And I'll say this one last time, please don't forget to look for conservation of energy. 2 things that will eventually become habit from this class: checking for conservation of energy and also checking for convergence. That is really the way that you're going to determine how many grid cells you need, what the grid resolution needs to be. Any kind of question you could say, well, how many of these do we need, or how small does that need to be? I can't answer that. All I can do is give you rules of thumb. You have to go look for convergence. So you keep adding cells to your grid, or you keep refining the grid resolution. At some point when the answer no longer changes that much, we say it's converged, and that's the rigorous way to find the answer. So that's finite difference frequency domain.